All right, the universal law of gravitation is what? So Fg is equal to big G m1 m2 over r squared. That is the universal law of gravitation. You must memorize it as such. Okay, what does your book call it? I mean, what does your formula sheet call it? Yeah. The potential energy of gravity, and it's actually usually called UG, is equal to big G m1 m2 over r. Because remember, work was force times distance, and if force is big G m1 m2 over r squared, and this is d, if d equals r, meaning the distance between the two objects is equal to the radius of that distance between the two planets or something, then that tells us that the work done to separate those two things is this. And if I take two things, I can say PEG is big G m1 m2 over r. And so now I just call out literally our big gun. Actually, I gotta make it smaller, otherwise I can't use it. There you go. All right, clear that. And so it's 6.67 times 10 to the minus 11 times 7.23 times 10 to the 22. No. What was the mass of the moon? 7.35 times 10 to the 22. Okay. Times 5.98 times 10 to the 24 divided by, whoops, just kidding. What is it? 7 point something? 7.38? 335? Wait a minute, what? What is the radius? See, I'm going through this formula.
3.84.
Oh, 3.84. Okay, 3.84 times 10 to the 8th. And boom, there's our answer. Which I lost. Sorry. 7.6 times 10 to, yeah, that was. You'll hear me sneeze. Oh, look, I can delete using that. Cool. That's cool. Can I do this? Oh, nice. I can use the keypad. All right, 7.63 times 10 to the 28. So the answer is 7.63 times 10 to the 28 joules. 7.63 times 10 to the 28 joules. That's for part A. This is going to be 1/2 m, and the velocity is going to be distance over time. So it's going to be 2 pi radius of moon to Earth over the time, which is 28 days times 24 hours times 3,600 seconds. I hate stoichiometry, yes. Okay, so then here, I wish it wouldn't keep turning off, that's annoying. So we say 2 pi times the radius of the Earth, that distance. What was that distance? 3.84 times 10 to the 8th. Divided by 28 times 24 times 3,600. If you want to be more accurate, it's not 28. It's technically like 27 and something, but who cares? Oh, and then that, ooh, fart knockers. That's supposed to be squared, isn't it? Oh well, this will be the velocity. It's so the moon is moving 1,000 meters per second. I'm going to square that. Huh? How could that happen? So square that. 997 squared. Oh, okay, that's weird. And then I'm going to multiply that by 0.5, and I'm going to multiply by the mass of the moon, which was what? 7.35 times 10 to the 22. So it's 3.65 times 10 to the 28 joules. 3.65 times 10 to the 28 joules. How does that compare to its potential energy? It's smaller. So the smallers have it. Because the kinetic... Using the equation for the orbital velocity, so we're going to get 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 kilograms over 3.85? The distance between the moon and the earth.
It was 3.84.
3.84? Okay, 3.84 times 10 to the 8th meters. And if we go back with this, we have the square root of 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th divided by 3.84 times 10 to the 8th. And we get 1,020 meters per second. Is that reasonably close to what we came up with before? What did we come up with before as our velocity? I thought we calculated the velocity of the moon somewhere. Oh, yeah, over here. This, I think we got like 997 or something. So 997 meters per second, 1,020, they're both around 1,000, so that's not too bad. Especially remember